Now here we are going to study in bit more detail about the trigonometric functions. So as mentioned here, we'll be studying the domain, range, period and graph of all the trigonometric functions. So just to recap about these function related terminologies, we know that a function can be considered as nothing but a kind of processing box, which accepts some input which we denote by x, and the output that comes out of the function we call it as, say, f of x, or sometimes that can be also called as y, right? So all the values of x that can be fed as an input to the function, so the set of all the allowed values of x that can go in as an input to the function constitute what is called as the domain of the function. That's called as a domain. Whereas what all output values can come out of the function, the set of all those output values is called as the range of the function. So in other words, what values the function can take, that is called as the range. Now period is something which relates with the periodicity, that is the function taking the same value again and again after a specific interval. So that is called as a period. So technically we show that if f of x plus capital T is same as f of x for some quantity t, then we call that quantity t as the period of the function. Now what it means is the function repeats its values after the period t. So it's clear that instead of just t, if you take any integer multiple of t, still the function will of course repeat its value. So therefore the smallest such values that can be added, the smallest possible value that can be added to x so that the function repeats, that is called as the fundamental period and not just period. Alright, so that function will have a fundamental period. Now we will see that the trigonometric functions are the periodic functions and their graph, if plotted on coordinate system, repeats after certain intervals. So let us now go into the details of all of these functions. Now to begin with, let us consider the sine function. Now let us see in detail how this sine function appears, or from where its graph comes. So now just to give the background, we have seen that the trigonometric functions were defined with the help of a standard circle, isn't it? So here is the center of the circle. Now let us consider a rotating vector that is initially horizontal, pointing in the positive x direction. Now if you consider the tip of that particular vector, okay, that makes angle of 0 degrees or 0 radians with positive x-axis, because that radius vector is completely flat, right? Now let us recollect, sine ratio is defined as the y coordinate divided by the radius. Now for the simplicity, let us take the radius of the circle as 1, so that we don't have that denominator term as such, and whatever is the y coordinate, same is the sine of that angle. So when the angle is 0, the y coordinate of this particular tip is 0, and therefore if we want to plot sine of angle theta on y-axis versus theta on x-axis, so therefore when theta is 0, the sine of 0 is also 0, because that is the y coordinate. Now let us make that particular vector rotate a little bit through an angle of 30 degrees. So when it is 30 degrees, the tip is little bit above the x-axis, so therefore here we have the y coordinate coming as 1 by 2, because sine of 30 degrees is 1 by 2. So if you consider the angle of pi by 6, that is 30 degrees, its tip will be at 1 by 2. Now let us raise that angle further up, and now it is 45 degrees. Now when it is 45 degrees, we know that sine of 45 degrees is 1 upon root 2. So therefore when it is plotted, we get that as 1 upon root 2. So therefore we have 1 upon root 2 for pi by 4, which is 45 degrees. And similarly we go on plotting the y coordinates of the tip of the rotating vector for various angles. Now when we have reached 90 degrees, we will have the radius completely vertical, and hence its y coordinate will be nothing but 1. Okay, so therefore at pi by 2, the sine of pi by 2, which is 90, that will be equal to 1. So therefore clearly this is how we will get a function. Now as the radius vector moves further in the second quadrant, you will see that the y coordinate would have of course reduced below 1. So therefore the graph will once again descend down and it will go in the negative region when the angle goes in the third quadrant, and so on. So this is how we get the graph of the sine function. Now if you want to see how the graph looks after the 180 degrees, that is pi radians, so this is how the graph of the function looks like. So let us redraw this particular graph so that we will see one full cycle of the sine function. So the sine function has the shape of a wave-like structure, which we typically call as sinusoidal wave or sinusoidally varying function. The topmost value is 1 and the bottommost value is -1. So the topmost value 1 is achieved at pi by 2, which is 90 degrees, and the bottommost value is achieved at 3 pi by 2, which corresponds to 270 degrees. Now the function starts off with 0 at angle 0, then it once again becomes 0 at pi, that is 180 degrees, and later on once again at 2 pi, and from this point onwards the function will repeat, simply because when that radius vector has rotated one full circle, when it goes ahead it will basically start tracing the same path again and again. So therefore, as it is clear from this particular figure, the interval of angle theta after which the function repeats itself, so from 0 to 2 pi, which is nothing but 2 pi radians. So this is the interval of angles after which the sine function will repeat. Now looking at the domain, that is, as we saw, domain is which input x can be allowed for sine. So that means on the x-axis, if you look at the graph, we see that the graph exists for all the values of theta, that is, for every angle theta there will always be some value of its sine ratio. So therefore domain is nothing but set of all real numbers which can go in as an input. Now if you consider the range, which is the set of all possible values that the function can take, and since we are plotting the function on y-axis, that means we have to look at on y-axis which values the function is taking. So clearly we see that the function lies between -1 to 1 only, isn't it? It does not go above 1 or it does not go below -1. And 1 and -1 themselves are also the permissible values, of course. So therefore range is a closed interval from -1 to 1. Now from the figure, as we just saw, the period of the function is nothing but 2 pi radians, right? And here is the graph of the function. So in this way we have studied the full detail of how the sine function can be plotted from where it is coming from. So that comes directly from the definition of sine and cos ratios as x and y coordinates. Okay. So let's go ahead and go through the remaining functions, that is cos x. Now here, doing the same exercise, we'll get the cos function to look like very much similar to sine function, with one important change, that it is shifted, isn't it? So it is shifted with a difference of pi by 2 radians or 90 degrees as compared with the sine function. So apart from that, other details are the same, that is cos function also lies between -1 to 1, then that also repeats with the period of 2 pi radians, because if you see the waveform, that will repeat itself after every 2 pi radians. Then the domain is once again the set of all real numbers, so that part is exactly same as the sine function. Moving on, let us see the tan function, that is tan x. Now here what happens is, as we know that tan x is nothing but sin x by cos x. Okay. So when we start plotting the tan function, that is, let's consider here pi by 2, pi, 3 pi by 2 and so on. Let us keep this basic framework ready so that we can plot the graph conveniently. Here we have for 0, minus pi by 2. Now what happens when angle increases from 0 to pi by 2? You see that its sine coordinate, that is the sine ratio, that is y coordinate, will go on increasing, whereas its cos component will go on decreasing, because its x coordinate on the rotating vector on that standard circle will go on decreasing. So therefore clearly as a whole, the tan of that angle will very sharply increase as we go from 0 to pi by 2, and at pi by 2, if you observe, the cos of 90 degrees is 0, so therefore the denominator becoming 0, since it's approaching 0, the tan of pi by 2 will not be defined as such, and it will be approaching the infinity. So therefore if we plot the graph will look like this. It slowly increases and then it approaches infinity as we come closer to pi by 2. Now after pi by 2, it will start off with the negative side, because the angle goes in the second quadrant where tan has to be negative. Now when we come between pi and 3 pi by 2, once again the tan is positive in the third quadrant, so that will once again repeat, and so on in all the directions. So looking at the graph, we observe that if we talk about the domain first, that is what values of theta or x here, the angle, is allowed. Here we see that the tan is defined for all the values except for pi by 2, 3 pi by 2 and so on, and then minus pi by 2, minus 3 pi by 2 and so on. So clearly for odd multiples of pi by 2, the tan function is not defined, because there the denominator is becoming 0. So that we write as all real numbers except the numbers of the form 2n plus 1 times pi by 2, where n is an integer. Because you know that if n is an integer, then 2n plus 1 will always represent an odd integer. So therefore an odd integer multiple of pi by 2 cannot be allowed as an input to the tan function. So therefore skipping those, all other values are the valid inputs. So those are the part of the domain. Now looking at the range, that is if you look at the y-axis, which values the tan is taking, so we see that the entire y-axis is covered with the function, isn't it? So tan can take any value from minus infinity to plus infinity. Now we never write infinities in close brackets, so we write them in open interval, or that can be also denoted by simply set of real numbers. Looking at the periodicity, it is clear that the period of tan is not 2 pi like sine and cos, but it is just pi as seen here. So minus pi by 2 to pi by 2, the interval is of duration pi radians, or if you want we can calculate from pi by 2 to 3 pi by 2, that is once again of the duration pi. So that's the period of tan x. Moving on, cot x is, as we know, that is cos x upon sin x. So that is very much similar to the tan, except that cot x will not be defined when here sin x becomes 0, and we know that sin x will be 0 when x is either 0 or whether it is pi or 2 pi and so on. So that means at integral multiples of pi, the cot will not be defined. So that means we have to remove the values of integer multiples of pi. That will give us the domain. Okay? So the graph of the function looks like the descending down graph. The tan was having ascending structures. Here it is descending structure like this. At pi by 2, the cot will be 0 because cos of pi by 2 is 0 and sin pi by 2 is 1. So this is how we get the graph of the cot function. Once again, as far as range is considered, it is spanning the entire y-axis. So that means the set of all real numbers is the range of the cot. And once again, the period is same as tan, which is pi radians. Let's go ahead and now look at the sec function. Now sec is 1 upon cos, and now here we see the similarity with tan, which was sin upon cos. So the values for which tan did not exist because cos x becoming 0, for the same values even sec x will not exist because here also cos x is once again present in the denominator, right? So therefore the domain of sec x is same as the domain of tan function. Now the graph of the sec x of course is bit different. It is not very much similar to the previous graphs. So here let us see how it looks like. Now sec x graph is looking like this. If you observe at 0, the value of the sec 0, that is 1 because cos of 0 is 1. But as we come closer to pi by 2, since cos of pi by 2 is 0, therefore the reciprocal of that will slowly approach positive infinity. So therefore sec is not defined for pi by 2. Now later on when we go to the second and third quadrant, it will be just the opposite in the negative direction. So therefore the graph will be similar in shape but opposite in direction. That will be the inverted thing. Right? So here the peak of that inverted thing actually comes at -1. And once again it will repeat. So clearly if we observe here, the graph of sec is either equal to 1 or above 1, or it is equal to -1 or below -1, but it will not lie between the area -1 to 1, both excluded. So that is where we have the range of the sec x. Coming to the domain, as we saw, it is same as the tan, that is discarding the odd integer multiples of pi by 2, all other values are valid. And if we consider the range, then from all the real numbers we have to subtract the portion of open interval -1 to 1. Except these, all other values will be present in the range of sec x. Now if you consider the period from the graph, it is clear that the period is 2 pi, right? Because the one half or one lobe is present in positive direction and another is present in negative. So therefore together they constitute one smallest piece of the graph which repeats itself. So therefore the period is 2 pi. And lastly, when we come to cosec x, the graph of cosec x is once again very much similar to sec x because the graph of sin x and cos x were similar to each other. In case of cosec, it will not be defined when x is 0 because that is when sin x, that is sin 0, becomes 0. So the denominator becomes 0. So the graph will be same as cosec x except that it will be shifted by 90 degrees difference. Right, so here it is pi, here it is pi by 2. At pi by 2 value of the cosec is 1, and at 3 pi by 2 value of the cosec will be -1. Alright, so here once again the domain is nothing but set of all real numbers except the integer multiples of pi. If you consider the range, once again it does not lie between -1 to 1. So that means r minus 1 to 1, and the period is once again same as the period of sec x, which is 2 pi radians. So now summarizing everything, we have on the next slide we have the summary of all these details of the 6 functions. So let us take a peek at all of these values. So here we see the functions with their domains, range and the period.